Welcome to my YouTube channel, Physics Matters. In the previous videos we talked about kinematics, which means the description of motion, so to say. And now in this video I will continue with a new topic called dynamics, which means we will talk now about the cause of changes in motion. And this is done by forces. So the topic about which we talk now are forces, and we will see what forces are, what kind of properties they have, and how we can calculate certain things with them. And we will start with the properties of forces. Yeah, so we discuss now what makes a force, so to say. So we can just take a look at any random object that travels with a certain velocity. Yeah, so let's suppose v1, and then after a certain time we can find that it has another velocity. Yeah, so let's suppose it travels now in this direction, so the direction has changed, as well as the magnitude. So v2 is the absolute value of v2 is larger or greater than the absolute value of v1. And then we can already define a force here according to what we observe, and this is change in speed or direction. Yeah, so if the magnitude or the direction changes, this can only happen if a force is applied to this object. And and another thing which a force can do, let's suppose we have here a ball, air balloon, for example, and we have two forces acting on this balloon, for example, one in this direction, F1, and another one in the opposite direction, F2. And the magnitude of these two forces is identical, which means the ball does not move at all, it stays on its position. But what we can find out after applying these forces, we can find out that our ball deforms. Yeah, so it actually gets a little bit broader. Maybe it will be squeezed in the other direction. But what we find out is that the minute we stop applying these forces, it goes back to its previous position. Yeah, so another property of force is that it can deform objects. So we can write deformation of objects. Yeah, and then we have to discuss. So these are the two points which makes it possible for us to identify that a force acts on an object. And then we have to quantify this as well. So we have to find a mathematical symbol for that, a formula symbol. And this is easy because it is just F for force. Yeah, this we will use later many times. And then, of course, we also have to define a unit for the force. And in this case, the standard unit is indeed given as Newton. Yeah, and the letter for this is just N. Yeah, and this is 1 Newton, named after Isaac Newton, the famous physicist. And then, of course, the force itself is a vector quantity, which means it has a direction and magnitude. And what we can do with these things, we will see now in the following examples. But before we come there, I would like to discuss a few types of forces that exist, just to get a feeling for that. And of course, there are fundamental forces such as gravitation, electromagnetic force, and so on. But these are also non-contact forces, but I don't want to discuss them now. We will discuss about them when we come to these topics in the future. Now I want to discuss only forces that we can observe in our daily life. And one important one from my point of view is tension. Yeah, so we, for example, have an object which hangs on a rope, which is connected to a ceiling, for example. Yeah, so here we have, of course, our gravitational force acting on this object, and this is, of course, acting on every point on this rope as well. So in this case, the rope can, for example, deform, but it has to, of course, compensate the force of the gravitation acting on this object, just to make sure that this object doesn't fall down. So in this case, we have tension along this wire or along this rope. And then another thing which is also, I think, important and also a daily life force which we can experience in our daily life, which is also sometimes wanted, sometimes not, and this is called friction. Yeah, so this just happens when you have two objects with a not ideal surface. Yeah, so when you go into the microscopic world, you can find that every object does not have an ideal surface. It just has this roughness, and when it is moving over the surface of another object, then actually you have these small bumps interacting with each other by just having contact. Yeah, and this at the end results in a force which is acting from one object to the other, and the object actually slows down, or it even does not move at all. Yeah, we have different type of frictions, but all this we will discover, of course, in a later stage. And then a third one, which I also think we observe a lot of time in our daily life, and this is buoyancy. And this, of course, happens when we have, let's suppose, any object filled with a liquid or a gas. For example, it could be a glass of water, and then we have an object in this glass, and then what we can find out is that we have on the one hand our gravitational force Fg pointing downwards, and on the other hand we also have force pointing upwards, and this could be or this is in this case our buoyancy, and we call that maybe Fb, and this points in the opposite direction. So, and then if the buoyancy is greater regarding the magnitude than the gravitational force, then this object starts to float or swim upwards. Or on the other hand, if the gravitational force is greater, then it sinks down. Let us talk about addition of forces. So, as we said, they are just vector quantities, so we can also add them up in the same way how we add up vectors. So what we can do, maybe we can just draw some random forces here. Let's suppose this is our force F1, and then we can draw another force with another color maybe in here, and this could be, for example, F2. Yeah, then if we want to add them up, we have to parallelly shift F2 to F1, to the tip of F1. And if we do that, then it will look actually like this, that we have here our force F1 and our force F2 will be here. And then our resulting force, and this we can maybe, so this is F2, and our resulting force, which we can maybe draw in green, would be in this case look like that. Yeah, and this is the sum of these two forces. And then we can have a look at some special cases, because I think from these cases we are also always learning the most. So let's suppose we have here a vector F1, a force F1 pointing in this direction, and then we have another force F2 pointing also in the same direction, and the magnitude of both forces is identical, which means that at the end we get a resulting force which when we add them up, so here this is our force F1 again, and here we have our force F2, and if we add them up, then our resulting force F3 is pointing into the same direction, of course. And also what we can say is that the magnitude F3 is exactly identical to F1 plus F2. And then, of course, we can also have the other possibility that we have two forces pointing in opposite directions. So let's suppose this is our force F1 and our force F2 pointing has the same magnitude again, but pointing into the opposite direction. then in this case both forces are compensating each other. Yeah, the net force will be actually 0. So we can write here F3 equals F1 minus F2 because we have them pointing in opposite direction, which means that at the end the resulting force is 0. So now we can also write down in general, yeah, so these are special cases, but in general, if we have n forces acting on one object and we have to add them up, then this is the same as if we write F net, the net force, is equal to F1, yeah, so these are all vectors of course, plus F2 plus and then up to any certain force Fn, and this we can also of course write as the sum of I equals to 1 up to n of all our individual forces Fi. So then this is a very important formula, of course. It just states how we can add up forces and that we can use vector addition, as I said before. So I want to highlight this, and now we can take a look at some examples. Okay, now let's take a look at an example. So let's suppose we have any object. Let's draw it here. And we have two people dragging this object in two different directions. Yeah, they are actually pulling it. So we have here two ropes connected to the center of this object. And then we have two forces here. One is pointing in this direction, and this we call maybe F1. And we have another force pointing in this direction, and this could be called F2. And what we can also say here in this regard is that the magnitudes of these two forces, F1 and F2, are identical. So F1 is equal to F2, but the directions are of course different. And now what we want to do, we want to calculate a force F3 pointing in this direction, and the magnitude of this force F3 we want to calculate, which is necessary to compensate these two forces F1 and F2 to make sure that this object does not move. It can deform, but it does not move. So in order to do that, we have to of course first calculate the resulting force of F1 and F2 pointing into the direction of F3. Yeah, so F3 has to, or the other way around, F3 has to point into the direction of the sum of F1 and F2 in order to compensate it, to make the net force 0. So what we can do, we can actually add these two forces up, and instead of shifting F2 to F1, we can also draw this parallelogram, which is a rectangle in this case, and it just makes the drawing a little bit easier and to identify what is going on. So now we can calculate the net force here of these two, and maybe we can call that F12, yeah, which means that now we have the sum of F1 and F2, and we want to write down now the vector sum, which is given as vector F plus vector F1 plus vector F2. And if we want to calculate the magnitude, of course, this can be done very easily. We have here 90-degree angle, so we can just simply use the theorem of Pythagoras, which means that we have here F1 squared plus F2 squared and then the square root of that. And since F1 is equal to F2, we can simply write here square root of 2 times F1 squared, and this is the same as square root of 2 times F1. And this makes sense. If they were pointing in the same direction, we would have a factor of 2. If they point in opposite direction, they completely compensate each other. The net force will be 0, and they will be balanced, so to say. And in this case, they are perpendicular to each other, so we have a factor of square root of 2, which is 1.4 times the individual force. And now the question is only, what is the magnitude of F3? And of course, this is very easy. So we can write here magnitude of F3, of the force F3. And of course, this has to be identical to the magnitude of F12 in order to compensate this. Yeah. Since we are not interested in the direction, we can ignore any kind of minus sign here. If we want to really write down the vector, we can also do the same. We can use trigonometric functions in order to do that. But here in this case, we only want to calculate the magnitude, and this has to be identical to this vector F12. And if we have especially two forces and we know the angle between them, then we can use the law of cosines to calculate the magnitude. And in order to do this, let us start with, again, two forces. Let's suppose one acting in this direction and the other one acting in this direction. It's not necessary that the magnitude is identical, so they can have any direction, any magnitude. And now we want to calculate the resulting force. And before we can do this, we have to define the angle between them. So this could be, for example, alpha. And if we want to add them up, again, we can use, we can either shift F2 to the tip of F1, or we can use a parallelogram. So in this case, it would look similar to this. And then we can now calculate our net force here in this direction. And in this case, we could simply call that again F3. And then we have the angle alpha here as well. And then we also have here an angle beta and also here an angle beta. So then we can write here the law of cosines, which is in general given as a square equal b square plus c square minus 2ab cosine beta. So we can see here the theorem of Pythagoras, a square is equal to b square plus c square, and then we have to subtract minus 2ab cosine beta. So this can be applied now to any triangle. It's not necessary that it has a 90-degree angle. So now we want to change this to the angle alpha that we have here. And if we want to do this, we can take one thing into account in a parallelogram, similar to a rectangle. We have the fact that beta, as you can see here, appears 2 times, and alpha also appears 2 times, and the sum of all angles has to give 360 degree. So we can write here beta is equal to 360 degree minus then 2 times this angle alpha, and then we have to divide it by 2 because, as I said, the angle beta appears 2 times. And if we then calculate this fraction here, this is the same as 180 degree minus 2 divided by 2 is 1 minus alpha remains in this case. So then we already have what we need. We know now cosine beta is equal to cosine 180 degree minus alpha, and 180 degree minus alpha, the cosine of this, because cosine is a symmetric function. In this case, this is the same as if we write minus cosine alpha. So we can write f3 is equal to f1 squared plus f2 squared plus 2 times f1 times f2 times cosine alpha. And then, of course, we have to also take the square root here. And because this is an important formula, I would like to highlight this and draw again a nice box around that. And we can make another example, of course. So let's suppose we have here again 2 forces. One is F1 pointing in this direction, for example, another one pointing in this direction. And then we want to calculate the third force, F3, which is the sum of these two. And we want to calculate not the direction, but we want to calculate only the magnitude. Then, of course, we need to know the magnitudes of F1, which is, for example, given as 10 Newton, and we need the magnitude of F2, which is given, for example, as 20 Newton. And then we have here our angle alpha, and this could be, for example, given as 30 degree. So then what we can do, we can calculate F3, which is identical to the formula that I have stated before. F1 squared plus F2 squared plus 2F1 F2 cosine alpha. And then this is given as 10 Newton squared plus 20 Newton squared plus 2 times 10 Newton times 20 Newton times cosine of 30 degree. And from this we have to then calculate the square root. And this at the end results to 29 Newton. So the force that we get at the end is larger than each individual force that we apply. And another thing which we can do with forces is decomposing them, as I mentioned before. So the next thing which we can discuss is decomposition of forces. So we can have here, for example, a force F, and we want to decompose it and split it up into other forces, F1 and F2. So for example, this could be our force F1, and this could be our force F2. And then when we add them up, they have to result in the net force F. Okay, and a typical example which one can give in this case is the inclined plane. So let's suppose we have here an object. Resting on an inclined plane under the angle alpha. And then we have, of course, the gravitational force pulling it downwards. So we have here our force Fg. And then we can split this up in two forces which are actually given by the symmetry of the problem. So in this case, for example, we have one force which points into the direction of the plane, which looks, for example, like this. And we have one force perpendicular to the surface of the plane, which could look, for example, like this. And then we have to, at the end, they have to add up to the resulting force Fg. And this one we call Fd, and this one here we call Fn. And then what we have here is this so-called downhill force, Fd, which is given. Now we have to find out where this angle alpha is. And we know that on the sides we have 90-degree angles, which means that our angle alpha is given here and also here. So now in this case we can use trigonometric functions in order to calculate this, and we know that the sine of alpha is given as Fd divided by Fg. So in this case we can write Fd is equal to Fg times sine alpha. And then we also have the normal force Fn, and this is then given as, in the same way, the gravitational force times cosine alpha, the weight of the body times cosine alpha. And also here we can make an example to get a little bit more familiar with that. So let's suppose we have here two walls, and we have two ropes connected to these walls. And here we have an object in the middle. And this object is pulled downwards by the gravitational force Fg. And what we want to calculate F1 and F2, which are the forces, the tension along these two ropes. Or it could be also wires. If this is a lamp, for example, then we have two wires here connected to this. So what we want to calculate here our force F1, and we want to calculate here our force F2 and the magnitudes from that. So what we can do, we can first of all define an angle alpha. So let's suppose this could be this one here, and because it's a symmetric problem, on the other side we have also the same angle alpha. And as I said before, they have to add up to the total force. Yeah. So what we can do, we can just draw again our parallelogram. Yeah. And now we can see that we have a symmetric problem. So what we can actually make a horizontal line here and split this up in two parts, the upper and the lower part, and the same FG is in both cases identical. Yeah. So now our angle alpha is also given here, alpha and also alpha here. And now we can write, or we can use trigonometric functions, in this case cosine of alpha, which is equal to half of the gravitational force, because we made this problem symmetric, divided by 2. And then we have to divide this by either F1 or F2. It doesn't matter, they are identical. So we can write here, this is equal to Fg half divided by F2. Yeah, and then we can calculate now directly F1, which is in this case equal to, we have to bring only F1 to the other side and then divide by cosine alpha, which means this is Fg divided by 2 cosine alpha. Yeah, and this is everything which we have to do. So the gravitational force divided by 2 times the cosine alpha gives us at the end the force F1 acting on the tension acting on wire 1, and F2 is identical acting on wire 2. And now we can take a look again on some special cases just to find out whether our results make sense or not. I always recommend to do that. So let's suppose we have an angle of 0 degree, which means our cables are just pointing downwards, perpendicular to the surface of the Earth. And in this case, if we insert our alpha here in this formula, we get cosine of 0 is 1. So this means our force F1 is just simply Fg half, or Fg divided by 2. Yeah, and this makes sense because every cable or every wire will hold half of the gravitational force, and the other wire will hold the other half. So in this case, this makes sense. So now we can also have a look at alpha equals to 90 degree, and cosine of 90 degree is 0. Yeah, so then our force F1 would be Fg divided by 0, and this is actually infinity. And this makes sense because now an angle alpha of 90 degree means that we hold these wires horizontally, and then this force which we have to apply in order to balance this gravitational force becomes extremely large until it reaches infinity when we reach alpha 90 degree. So the last special case which we can have a look at is alpha equal to 45 degree, and then F1 is equal to Fg divided by 2, and cosine of alpha is cosine of 45 degree is 1 over square root of 2. So square root of 2 we can write in the numerator, and square root of 2 divided by 2 is the same as 1 over square root of 2, so this would be identical to Fg divided by square root of 2. And this makes also sense. So in this case, it's not half of the weight which every wire has to carry, but only by a factor of square root of 2 less. Okay, and this is everything which I want to tell you in this video. I hope that you liked it and you enjoyed it. And you also learned something new. Yeah, and then hopefully see you soon for a new video. Thank you very much for watching this video. If you like the content and want to see more of it, please like and subscribe. And in addition, any kind of support is always appreciated.